2 years. For 2 years, the most powerful telescope ever built has been showing us something nobody could explain. Hundreds of tiny red objects scattered across the early universe. Objects that shouldn't exist. Objects that broke every model we had for how the cosmos got started. Astronomers gave them a casual name, little red dots. And as of this week, we finally know what they are. But the answer raises a question that nobody expected. One that connects directly to something we talked about very recently on this channel. Let me explain. The James Webb Space Telescope launched on Christmas Day 2021. It took about 6 months to unfold its sunshield, cool its instruments, and calibrate its mirrors. And when it finally opened its golden eyes to the universe, one of its main jobs was straightforward. Look as far back in time as possible. Find the first galaxies. Find the first black holes. Tell us how the universe went from a hot, smooth soup of particles to the structured, galaxy-filled cosmos we see today. Nobody expected it to find something entirely new. When JWST started sending back its first deep-field images in 2023, astronomers noticed something strange. Tiny red specks everywhere. They were compact, they were red, and they were absurdly far away, existing when the universe was less than 1 billion years old. By 2024, they had a name, little red dots, and by 2025, there were over 340 of them cataloged. The name sounds cute, almost dismissive, but these things were causing genuine panic in astrophysics departments around the world. Because no matter what theory you threw at them, something didn't fit. First guess, maybe they're massive star-forming galaxies, huge clusters of young stars burning hot and bright. Problem is, galaxies that massive shouldn't exist that early. The universe was barely 700 million years old. There simply wasn't enough time for that much matter to clump together and start forming stars at that scale. Our cosmological models said no. Second guess, maybe they're quasars, the ultra-bright cores of galaxies powered by supermassive black holes, gobbling up everything around them. That would explain the brightness. But quasars blast out X-rays. Little red dots? Almost no X-rays. Quasars have steep infrared spectra. Little red dots? Flat. Quasars vary wildly from one to another. Little red dots? Weirdly consistent. They look like quasars from one angle, and absolutely nothing like quasars from another. There were other ideas too. Population 3 superstars, quasi-stars, slowly spinning dark matter halos. Each one explained a couple of properties, but fell apart on the rest. It was like trying to identify an animal from its footprint, its call, and its diet, and getting 3 different species every time. And then there was the really uncomfortable part. If these things did contain black holes, those black holes were enormous. Millions, sometimes billions of times the mass of our sun, existing when the universe was a cosmic infant. Here's the problem in plain language. In the standard model, black holes start small. A massive star burns through its fuel, collapses and leaves behind a black hole of maybe 10 to 100 solar masses. That's your seed. Then, over billions of years, that seed grows. It eats gas, it merges with other black holes. It slowly, painfully accumulates mass. But 1 billion solar masses in a few 100 million years. 1 billion suns worth of mass, compressed into a region smaller than our solar system, existing when the universe had barely gotten started. Even if you feed a black hole at the absolute theoretical maximum rate, what physicists call the Eddington limit, the math just does not work. You cannot grow a 10 solar mass seed into a 1 billion solar mass monster in the time available. So either our understanding of black hole growth is fundamentally flawed, or these black holes didn't start small. They were born big. For years, theorists had whispered about a mechanism that could do exactly that. A way to skip the entire slow growth phase and create a massive black hole from scratch. But it remained theoretical, a neat idea on a whiteboard. Nobody had proof. Until this week, that is. On January 20th, 2026, Fabio Pacucci at the Harvard Center for Astrophysics, along with Andrea Ferrara and Dale Kachevsky, posted a paper with one of the most confident titles I've seen in astrophysics. The little red dots are direct collapse black holes. Not might be, not could potentially represent, are. The paper is currently under review at Nature. So what is a direct collapse black hole? In the very early universe, before the first stars had seeded space with heavy elements, there were pockets of pristine gas, pure hydrogen and helium. No metals, no dust, no complexity, just clouds of primordial material sitting inside structures called atomic cooling halos. Normally, when a gas cloud starts to collapse under its own gravity, molecular hydrogen helps it cool down and fragment into smaller clumps. Those clumps become stars. Stars live and die, and some leave behind small black holes. That's the normal path. But if something prevents molecular hydrogen from forming, say intense ultraviolet radiation from a nearby galaxy bathing the cloud in light, then the gas can't fragment. It can't cool efficiently. It can't form stars. Instead, the entire cloud, we're talking tens of thousands to a million solar masses of gas, collapses directly, all at once, into a single massive black hole. No star phase, no slow growth. The black hole is born massive. Think about the difference. In the standard model, you're starting with a marble and trying to build a boulder by rolling it through sand. With direct collapse, the boulder just appears, fully formed, ready to grow even bigger from there. These direct collapse black holes have been theoretically predicted for decades, but nobody had ever found convincing observational evidence for them. Until now. What Pacucci's team did was build radiation hydrodynamic simulations. They modeled both the gas falling onto these newborn massive black holes and the radiation that gas produces as it falls. They tracked how the radiation bounces around, gets absorbed, gets reprocessed. And then they compared their simulated observations to what JWST actually sees when it looks at little red dots. The match was, in Pacucci's own words, incredibly well. And not just for one property, for all of them. Every single puzzle that had been driving astronomers crazy for 2 years fell into place at the same time. Why no X-rays? Because the dense accretion flow around the direct collapse black hole absorbs the high-energy radiation before it can escape. Why metal lines but no star formation signatures? Because all the emission comes from the black hole's reprocessed radiation. There are no stars contributing at all. The ultraviolet light we see is entirely from the black hole. Why are the black holes so overmassive? Because they were born that way. Why are they so compact? The dense gas cocoon surrounding the black hole makes the entire structure appear tiny. Why are there so many of them at specific cosmic ages? Because they're linked to pristine gas halos, which were common in the early universe and became rarer as stars polluted everything with metals. Why do they last so long and change so slowly? Because radiation pressure from the black hole itself regulates the accretion, creating stable phases lasting over 100 million years. 6 puzzles, 1 model, no ad hoc assumptions, no extra ingredients, just physics playing out exactly as theorists had predicted decades ago. As Pacucci put it, our results suggest that JWST is witnessing exactly this long-sought phase, the formation and growth of massive black hole seeds through direct collapse. This would be a major breakthrough, showing that the earliest black holes formed efficiently and early, and that JWST is finally opening a direct observational window onto their birth. Let that sink in. One of JWST's primary goals was to find the first black holes and understand how they formed. And according to this paper, it's been staring at them for 2 years. We just didn't know what we were looking at. This is the kind of result that makes you sit back in your chair. For 2 years, hundreds of astronomers looked at these little red dots and argued. Massive galaxies? Weird quasars? Primordial superstars? And the answer was something predicted theoretically for decades but never observed. Black holes that skip the line, born directly from the primordial gas of the early universe. Now, here's where this story takes a turn. If you've been watching this channel, you might remember a video we did very recently about a paper published on February 5th in the monthly notices of the Royal Astronomical Society. A paper by Valentina Crespi and an international team of astrophysicists arguing that Sagittarius A star, the 4 million solar mass object at the center of our Milky Way, might not be a black hole at all, that it could be an ultra-dense core of fermionic dark matter mimicking a black hole's gravity so perfectly that even the Event Horizon Telescope's famous shadow image could be reproduced without an event horizon. If you haven't seen that video, go watch it after this one. I'll link it below. It's important context for what I'm about to say. Here's what matters for today. That paper dropped on February 5th. Pacucci's paper hit the news on February 8th, 3 days apart, and I'm almost certain neither team was thinking about the other. So in the same week, February 2026, two papers. One proves that hundreds of objects in the early universe are definitely massive black holes, born through direct collapse. The evidence is spectroscopic, emission-based, and extremely specific. The other argues that the single object we were most confident was a black hole, the one we literally photographed, the one that won a Nobel Prize, might be something else entirely. Now, some of you are already a step ahead. If Sagittarius A star might not be a black hole, could the little red dots also be dark matter instead of black holes? And the answer is almost certainly not. And the reason why is exactly what makes this whole situation so fascinating. Remember from our previous video, the case for Sagittarius A star being dark matter works because the evidence there is almost entirely gravitational. Stars orbit something massive. Gravity bends light around it. A dark matter core can produce the same gravity and the same light bending. There's no way to tell the difference from gravity alone. But little red dots are a completely different story. They're not just heavy. They glow. They emit very specific spectral fingerprints. Broad Balmer emission lines from hydrogen gas moving at extreme speeds. Metal lines from ionized elements. A UV continuum that Pacucci's team showed comes entirely from reprocessed black hole radiation. These are the signatures of matter actively falling onto a compact object and releasing energy as it spirals in. A dark matter core, no matter how dense, doesn't accrete matter the same way. It doesn't produce those emission signatures. The physics of a fermion ball sitting there, even an incredibly dense one, is fundamentally different from a black hole with an accretion disk eating everything around it. So we end up in this genuinely bizarre situation. The distant objects, 13 billion light years away, have emission evidence that pins them as black holes. The nearby object, 26,000 light years away, the one we've studied for decades, has mostly gravitational evidence that could go either way. We might be more certain about what's happening in the infant universe than about what's sitting in our own cosmic backyard. And the irony cuts even deeper. Pacucci's paper essentially demonstrates what definitive black hole evidence looks like. It's emission-based, it's spectroscopic. It shows specific radiation signatures that can only come from accretion onto a compact object. That's the gold standard. And it's exactly the kind of evidence that Sagittarius A star's case is weaker on. The evidence there is gravitational. Stars orbiting something massive. Light bending around something dense, which, as Crespi's team showed, a dark matter core can replicate. Think about what that means for the field. One team just raised the bar for what counts as proof of a black hole, and by doing so, they may have inadvertently highlighted why the evidence for our own galaxy's central black hole isn't as airtight as we assumed. Now, let me be fair about the limitations. Crespi's team acknowledges that current data cannot decisively distinguish between the two scenarios for Sagittarius A star. Upgraded instruments like Gravity Plus and the Next Generation Event Horizon Telescope will look for photon rings, which black holes should produce and dark matter cores should not. That's the test. And Pacucci's paper, while remarkably comprehensive, is still under peer review at Nature. The scientific community will scrutinize it heavily. There will be alternative interpretations. There will be objections. That's how science works. The model is elegant and explains a lot, but elegant doesn't always mean correct. We've been fooled before, but if both papers hold up, the implications reshape how we think about black holes entirely. First, JWST has achieved one of its primary scientific goals, finding the first black holes. Direct collapse. Black holes are no longer theoretical, they're observed. Second, black holes in the early universe were born big, not grown. Born. That rewrites every model of galaxy formation and how galaxies and their central black holes grew up together. Third, the early universe was wilder and more creative than we imagined. Hundreds of massive black holes forming directly from pristine gas, lighting up as little red dots across the cosmic dawn. The first few 100 million years after the Big Bang weren't the quiet, dark period we assumed. They were a factory floor, churning out monster black holes from raw hydrogen. And fourth, we might need to get much more careful about how we identify black holes going forward. Gravity alone might not be enough. You need the emission evidence, the spectral fingerprints, and that standard was just set by a paper about objects 13 billion light-years away. Two papers, same week. One proves distant objects are definitely black holes. The other questions whether our closest one is real. Sometimes the most unsettling discoveries aren't the ones that reveal something new. They're the ones that make you question something you thought was already settled. And right now in February 2026, black hole science is doing both at the same time. Want more of the latest science that keeps rewriting what we thought we knew? There's always another paper, and lately they keep coming in pairs.